Good morning, good afternoon, and good night to everybody. This is my first lectures on course Physics 1 and the basic concepts of physics, including mechanics. And in this lecture, we will discuss what is physics, fundamentals of physics, work, power, energy, Newton's law of motion, conservation of energy, linear momentum, rotational motions, oscillatory motions, gravity and gravitations. So, and we also discuss about some real life examples of physics connecting these topics. Now, welcome to my class. So, first of all, the best physics, the basic of science, and in this part, we will discuss about the um, physics. First of all, what is science? A body of knowledge growing all the time, and human activity and a body of knowledge, systematized body of knowledge based on nature and facts of life, or general principles of foreign to observable common sense statement. Actually, science it is a knowledge of any body growing all the time. So actually, this is the part of a philosophy, and philosophy is divided into two parts. One is natural philosophy, and other is physics. Ethics. Physical science can be divided into three parts: physics, chemistry, astronomy, and biological science, botany, geology, and ecology. So, what is the physics? First of all, this is the branch of science which deals with the study of matter and energy. So we have to remember that this is a branch of science and deals about the matter and energy. So this is the main branch of science. Now, branches of physics, what will be? First of all, the mechanics. And mechanics, the founder of actually mechanics, considered as the father of physics, Sir Isaac Newton, and so mechanics, it actually the work of Newton. So mechanics, Newtonian physics also, and force and motion, kinematics, description of motion, dynamics, description of causes of changes in motion. So uh, mechanics can be divided into two parts. One is dynamics, another is statics. So branch of physics also is thermodynamics, which is relationship of heat and mechanics, which includes through study of energy. So, and branches of physics, another one is waves. Waves means you must know deals with how energy is transferred. That includes the concept of light, sound. You must know light, which comes from sun, and sound we must know about this. So this is the this is another important part of branch of physics, and waves, which will be deals with the how energy is transferred. That includes concept of light and sound. Actually, the real life example of waves is we are talking with each other, and you are hearing my lecture, and I am talking about the branch of physics. This is the actually combination of sound and also energy. Now, another branch of physics is electricity and magnetism, deals with characteristics and behavior of matter. So, you must know electricity. We always use this electricity. Using this electricity, we are talking about, we are taking lecture in online. And you also magnetism. Magnetism is the properties of a magnet. So, deals with the characteristics and behavior of matter. Another one branch of physics is relativity and modern physics, which deals with the concept of covered in the first four branches, which not covered in the first four branches. Actually, this is the fifth branch, and this is the this related to Einstein's theory. Okay, relativity and modern physics. Now, scientific method, a method that is extremely effective in gaining, organizing, and applying new knowledge. So, scientific hypothesis, scientific law. Actually, this is included in physics, and scientific facts and scientific theory, close agreement by competent observers of the same phenomena. And scientific theory is a synthesis of a large body of information that encompasses well tested and verified hypotheses about the certain aspects of the world. So tools of science, you must know mathematics is the language of science. So first of all, the language and the mathematics. Now physical quantities that describes matter can be classified into fundamental quantities or derived quantities. Okay, we'll study about this in our next slide. First of all, physical quantities. First of all, physics, it is the science of phenomena, of properties of matter and of the forces governing it. Then we will discuss about the measurement. What is measurement? Determining the quantity of something is called measurement. Measurement means you must know the porimap. For example, 3 kilograms sugar, 500 meter, etc. Now, what will be the unit? Unit means ekok. The ideal and standard quantity comparing with which physical quantities are measured is called unit of measurement. What is unit of measurement? For example, unit of distance is meter, mass is kilogram, and another one is physical quantity, anything that is measurable in the physical world, which can be measured in the physical world is called physical quantity. Now fundamental quantities, you must know fundamental quantities, the physical quantities which are independent, that do not depend on other quantities, rather other quantities depend on them, are called fundamental quantities. There are 7 number of fundamental quantities: length, mass, time, temperature, electric current, luminous intensity, amount of substance. So you must know that the unit we use in physics are internationally agreed and recognized in 1960. So the fundamental units of is called, another one is SI units, system of units. Okay, the standard of fundamental units that were accepted in 1960 were introduced in SI unit, system of units. So here the SI implies that international system of units. The physical quantities: length, symbol is L, unit is meter, and symbol also, symbol of meter is M. Mass means symbol is M, and kilogram, mass unit kilogram, and symbol is kg. So this is the 7 fundamental units: time unit second, temperature units Kelvin, electric current unit ampere, luminous intensity candela, and amount of substance is co. This is the Padarthir Purima. And now CGS units and FPS units, centimeter, gram units, and FPS means foot poundal system, pound system. So these two types of, there are 2 types of units. And quantity, derived quantity, what? The quantity which depends on fundamental quantities or be derived from fundamental quantities are called derived quantities. Now you must know velocity, acceleration, force, weight, etc. are derived quantities, because force is the derived quantities because it depends on 3 fundamental quantities. One is mass, another is velocity, another is time. So this is the actually basic concepts of measurement. So we must know about the what is measurement. Okay, and so measurement in everyday life, you must know about this, the measurement of masses, uh, uh, Bohrer porimap, and measurement of volume, actually oil, kerosene, etc. We are measuring with volume. So measurement of volume, this we use in everyday life. And measurement in everyday, measurement of length, when you want to buy a cloth or so in tailors, from tailors. So you must measure your body length. This is the measurement of length and measurement of temperature. When you are feeling fever, then you have to measure the temperature in clinical thermometer. So needs for measurement in physics. To understand any phenomenon in physics, we have to perform experiments. Experiments require measurements, and we measure several physics properties like length, mass, time, temperature, pressure, etc. Experimental verification of laws and theories also needs measurement of physical properties. So we must know what is the physical quantities. A physical property that can be measured and described by a number is called physical quantities. And this is the example: mass of a person is 65 kilogram, length of a table is 3 meter, etc. The example of physical quantity. Now, types of physical quantity: fundamental quantities and derived quantities. The fundamental quantity, the physical quantities which do not depend on any other physical quantities, uh, rather other quantities depend on them. This is called fundamental quantities. There are 7 types of fundamental quantities, you must know. Now, types of physical quantities: derived quantities. The physical quantities which depends on one or more fundamental quantities for their measurements are known as the derived quantities. So volume, speed, force, etc. So units of for measurement, the standard used for the measurement of the physical quantity is called unit. So what is unit? What is unit? That means eকক কাকে বলে? The standard used for the measurement of physical quantity is called unit. So meter, foot, inches, etc. for length, kilogram, pound for mass, second, minute, hour for time, Fahrenheit, Kelvin, etc. for temperature. This is the main example. The characteristics of any well-defined, suitable size, reproducible, invariable, indestructible, internationally acceptable. So this is the CGS system. You must know about this. Centimeter, gram, second. Another is MKS, meter, kilogram, and second. Okay, and FPS, foot, pound, second. You must know about this. Is the actually used in Britain and British system also. So SI units, you must know, in 1961 we use this system of units. There are 7 types of fundamental units, you must know: length, mass, দৈর্ঘ্য, ভর, সময়, তাপমাত্রা, তড়িৎ প্রবাহ, etc. Definition of meter, you must know what is meter. This is the definition of from the very beginning. So, and definition of kilogram also. This is now we'll discuss what is the scalar and vector quantity. What is a scalar? First of all, actually scalar, this is the quantity which expressed with the magnitudes only. Now, length of a car is 4.5 meter. Length is the physical quantity and 4.5 is the magnitude only. So the expression and the quantity which can be expressed with magnitudes only is called scalar quantity. And the mass of a gold bar is 1 kilogram. So physical quantity is mass here and 1 kilogram is magnitudes. Similarly, time is 12.76. So time is the physical quantity and this is the magnitudes only. Similarly, temperature is 36.8 degrees centigrade. Here physical quantity is temperature and magnitudes is 36.8. So first of all, what is a scalar quantity? A scalar is a physical quantity that has only magnitudes. This is the example: mass, length, time, temperature, volume, density, etc. Similarly, what is vector? Now, position of California from North Carolina is 3600 kilometer in west. Actually, this direction included with that two parts. One is magnitudes and another is direction.
So the physical quantity position of California depends on direction and magnitudes. So the quantity which can be depends on direction and magnitudes is called vector quantity. So what is vector quantity? The vector quantity and the quantity which can be expressed with the direction as well as magnitudes is called vector quantity. Similarly, the displacement from USA to China is 11,600 kilometer in east. So here physical quantity is displacement, east is the direction, and 11,600 kilometer is the magnitudes. So the quantity which depends on direction and magnitudes is called vector quantity. So now the definition, what is the vector quantity? A vector is a physical quantity that has both a magnitudes and a direction. For example, position, displacement, velocity, acceleration, momentum, force, etc. Now, a representation of a vector. Now, this is the AB is a vector, and the distance will be the magnitudes, and head is B here, and tail is A. This is the angle which indicate the direction. So symbolically, it is represented as AB vector. Okay, with the arrow sign, we can denote as a vector. Now, representation of a vector, they are also represented by a single capital letter with an arrow above it, a vector, B vector, and P vector also. Now, representation of a vector, position vector can be expressed as R vector, and velocity V, and force F. Types of vector on the basis of orientation. This is a parallel vectors, A vector and B vector direction same, but length may be different. Similarly, P and Q also parallel. Equal vectors, the two vectors will be equal. It will be equal in length and direction. So anti-parallel means you must know a vector and the opposite, the direction of another vector will be in opposite of a. Similarly, PQ is the also anti-parallel. Now, negative vectors, what will be? A vector can be expressed as the another vector B with the negative. So A vector and B vector will be equal but opposite. Similarly, P and Q also. Now, collinear vector, A vector and B vector will be collinear if they are two vectors are said to be collinear vectors if they act along the same line. Okay, P and Q and F. Co-initial vectors, two or more vectors are said to be co-initial vectors if they have common initial points. Suppose A vector, B vector, C vectors, and D vectors which pass through the same points. That means the initial points. Co-terminal vectors, two or more vectors are said to be co-terminal vectors if they have common terminal points. A vector and B vector, C vector. Then all vectors are meeting at a point, co-terminal. Coplanar vectors, three or more vectors are said to be coplanar vectors if they lie in the same plane. Okay, A vector, B vector, C vector, D vector lie in the same plane. Non-coplanar vector, three or more vectors are said to be non-coplanar vectors if they are distributed in the this is the coplanar vectors. Three or more vectors are said to be non-coplanar if they are distributed in same space, not in same plane. So this is the non-coplanar types of vectors on the basis of effects. Now, polar vectors. Vectors having straight line effects are called polar vectors. For example, displacement, velocity, acceleration, force, etc. Axial vectors. Vectors having rotational effects are called axial vectors. Suppose angular momentum, angular velocity, angular acceleration, torque, etc. So now vector addition geometrically. Triangle law. Suppose Iran, Egypt, and Yemen. We are connecting with Egypt to Yemen and Iran to Yemen is B vector. So if their distance from Egypt to Iran will be indicated by C vector. So C vector can be represented as A vector plus B vectors. This is the triangle law. Similarly, parallelogram law. And suppose A vector, and this is the A vector, and another one is B vector. So A vector and B vector acts at a point, same points. Suppose this is a pulley and having with a mass m. So if A vector and B vector can be represented as this diagram, like a parallel. So A vector and this is the another parallel, equivalent parallel lines. So this C vector, that means the sum of these two vectors will be indicated as, that means resultant will be the A vector plus B vector. This is the parallelogram law. Similarly, polygons, this is the actually wheel of a car or any vehicle. So at a point, A vector, B vector, C vector, and D vector are coming from the same point. Then after addition will be this addition of these four vectors will be polygon law. We have to use polygon law. C vector equals to A vector plus B vector plus C vector plus D vector. Then with A vector, this is the initial and this is the final point. Adding another second vector with the first. So A vector plus B vector plus same direction. All are same direction, but resultant will be the opposite direction. So E vector equals to A vector plus B vector plus C vector plus D vector. Similarly, vector can maintain the commutative law. A vector plus B vector equals to will be B vector plus A vector. And associativity also maintains in vector. So the addition of vectors obey the associative law. Similarly, subtraction of vectors, A vector plus, minus B vector will be indicated as like this. So A vector minus B vector will be A vector plus addition with the opposite of B. So this is the magnitudes of result or resultant. You must know about this. Resultant R equals to in of A vector of P vector and Q vector can be expressed as root over P square plus 2s PQ cos theta plus Q square. This is the resultant of magnitudes. Now, similarly, direction can be found like this: sin theta equals to perpendicular by hypotenuse. So, cos theta equal to base by hypotenuse. Similarly, tan means tan alpha equals to perpendicular by base. So, base OM equals to what? OA plus M. Just putting the value of OA and M, we can find the direction. Similarly, two parallel vectors. If the angle between them is theta equals to 0 degree, then the magnitudes will be the maximum and direction will be 0 degree. Similarly, if theta equals to 90 degree, then magnitudes will be root over P square plus Q square, and alpha equals to tan inverse P by Q. If the vectors are anti-parallel, that means theta equals to 180 degree, then the magnitudes will be the minimum. So, and if the first vector is greater than the second vector, then alpha equals to 0, and the first vector is less than the second vector, then including angle will be 180 degree. This may be indicated as force also. So unit vector, what is unit vector? Unit vector is a vector that has the magnitudes of exactly 1 and drawn in the direction of a given vectors. Okay, a vector and another vectors. It lacks both dimension and unit. It has only purpose is to specify a direction in the space. Unit vectors, you must know the unit vectors. A given vector can be expressed as a product of its magnitudes and a unit vector. For example, a vector can be represented as like this. Cartesian units of vectors, you must know, along the x-axis I, along the x-axis I, along the y-axis is z, and along the z-axis is the k. So I, j, k, this is the red color and green. So these three colors indicates the unit vectors along the x-axis, y-axis, and z-axis. So resolution of vectors, you must know, it is the process of splitting a vector into two or more vectors. From one vectors, we can split into it into two parts. One is n, another is at. So along the t, at, and along the n, n. So one vectors can be expressed in or represented into two or more vectors. So rectangular components of 2D vectors, you must know, vectors can be represented as x along x-axis and along y-axis. Ij is the unit vectors. Similarly, we can find the angle also using sin theta equals to sin theta equals to base by hypotenuse. So cos equals to perpendicular by hypotenuse sine and base by hypotenuse is cos. So we can find the value of x vectors, and another one is ay vectors. Magnitude and direction from components, a vector can be represented as like this. Magnitudes will be root over x square plus ay square, and angle will be tan inverse ay by x. This is the resultant along x-axis and the resultant along y-axis. This is called also upangsha. X-axis এদিকে upangsha and y-axis এদিকে upangsha. This is the magnitudes মান এবং direction দিক. Rectangular components for 3D vectors, you must know this is the x along x-axis, y along y-axis, and az along z-axis can be represented as like this: a vector equals to x vector, a y vector, and plus az vector. So similarly, in 3D vectors, the direction can be always like this. Now, rectangular vectors, components of 3D vectors, can be represented as along the y-axis, a cos beta. Similarly, on z-axis, z equals to this. Now, magnitudes and direction from the components, you must know magnitudes can be represented as a vector equals to root over x square plus y square plus az square, and direction will be this: alpha equals to this, beta equals to this, and z gamma equals to this. Now, adding vectors by components, you must know a vector and b vector can be take the resultant r equals to a vector plus b vector. Okay, just adding. Now, multiplying vectors, multiplying a vector by a scalar, and multiplying vector by a vector also. So there are two types of multiplication here. Now, if s is the positive, then 2 times will be like this. If s is negative, 3 times will be like this. Just opposite of a, because negative. Now, multiplying a vector by a vector, these are two types. One is dot product, and other is cross product. One is the dot product depending on cos theta, and cross product depending on sin theta. This is the scalar product. The example of a scalar product is work done. Work done equals to what? Displacement multiply force. So a vector dot b vector equals to ab cos theta. Okay, and this is the example of a scalar product. This is the work done, force, dot product, displacement. So work done, force, displacement. Similarly, power, force, velocity. Okay. The geometrical meaning of a scalar and vector product. Now, vector product can be represented as the projection of a on b vector. Okay. Properties of the scalar product: a dot b equals to ab cos theta and b dot a equals to ab. So maintain the associative commutative law. Similarly, 3 properties of this is also another properties. Number 3 properties. The scalar product of 2 perpendicular vectors is 0. Cos 90 degree equals to 0. This is why a dot b equals to 0. So similarly, the scalar product of 2 parallel vectors will be cos 0 equals to 1. This is the maximum positive. Similarly, the maximum negative will be at anti-parallel. That means 180 degree, including angle will be 180 degree. Cos 180 degree equals to -1. This is why a dot b equals to -ab. This is the maximum negative. Similarly, the scalar product of a vector with itself is equal to the square of the magnitudes. Okay, that means same vectors. If we take the dot product of same vectors, then it will be a square. Similarly, I dot I, z dot z, k dot k equals to 1, because I dot I means what? Including angle 0 degree. So cos 0 degree equals to 1. This is why 1 into 1. This is the unit vector. This is why 1. Similarly, I dot z, z dot k, k dot I equals to 0 degree, because they are perpendicular to each other. Now, calculating the scalar product using components, a dot b will be what? Just multiplication. And you must know I dot I, z dot I dot z equals to 0, I dot k equals to 0. In this, using this relationship, we can find the a dot b equals to x bx plus ay by and az bz. Now, another important product of vector is vector product. So depending on sin theta, a cross b equals to ab sin theta. This theta indicate the direction of the vector product. This is indicated as c vector. Now, how do we indicate the the direction of vector product. This is the right hand rule. At including angle will be theta, but the resultant will be the c. So direction will be like this, right hand rule. Similarly, torque is the example of the vector product. Torque is the you must know torque equals to position vector vector product with the force. So tau equals to torque equals to Rf sin theta. This theta indicates the direction of tau. That means similarly, angular momentum L equals to what will be position angular or radius multiply P. P means linear momentum. So L can indicate Rp sin theta theta. Theta is the actually indicate the direction. Similarly, geometrical interpretation, we can actually the vector product. The magnitudes of a vector product will be the area of the parallelogram made by two vectors. Similarly, properties of vector product, A cross B equals to AB sin theta. So B cross A equals to minus AB sin theta. This is why it cannot maintain the commutative loss. Now, properties 2, vector product is the vector product is distributive over addition. Okay. Similarly, A cross B magnitudes of the vector product will be AB sin 90 degree. 90 degree means what? This is the 1. So this is the maximum. So perpendicular to perpendicular vectors gives the maximum magnitudes. Similarly, the vector product of two parallel vectors is a null vector because sin 0 degree equals to 0. This is why this is the minimum. Now, property 5, the anti-parallel vectors will be indicates the A cross B equals to also 0. Similarly, the vector product of a vector with itself is a null vector. Okay, A cross A equals to A sin, because the including angle is 0 degree. This way sin 0 equals to 0. This way 0. Property 7, I dot I, Z dot Z, and K dot K equals to actually 0. Similarly, I cross Z equals to K, Z cross K equals to I, K cross I equals to Z. But if they are, because the vector product cannot maintain the commutative loss, this is why Z dot I will be minus K, K dot Z equals to K cross Z equals to minus I, and I cross K will indicate minus Z. So remember this I, Z, K. This is the actually sequence for counting I, Z, K. But if this circle or represented like this, then it the anti sequence, then it will be indicated as minus here. Okay. So calculating cross product of two vectors, just putting the values of this one, we can find the calculation of the product of two vectors. Now calculating the product of three vectors, two vectors, one is A cross B equals to this. This is actually determinant of Izk, Ax, Yz, and Bx, By, Bz. This is the first vector, second vector. Components of first vectors is the second row, and second vector will be the third. So this is actually this is the complete description with a real life example of that. So from this part, we can define what is a scalar quantity. Physical quantities which can fully expressed by magnitudes only are called scalar quantity. So length, mass, speed, work, energy, time, etc. Are the example of scalar quantity. Similarly, vector quantity, what should be physical quantities which need both magnitudes and direction to be fully expressed. It's called vector quantity. Now, displacement, weight, velocity, acceleration, force, etc. are the examples of vector quantity. What is the difference between scalar quantity and vector quantity? You must know about this vector quantity. And now, what will be the speed and velocity? Motion in physics, motion is a change in position of an object with respect to time. So, what is motion? This is the definition of motion. Motion in Bangla, goti. Change in action is the result of an unbalanced force. Motion is typically described in terms of the velocity, acceleration, displacement, time, etc. Now, what is linear motion? Also called rectilinear motion, is a motion along a straight line and can therefore be described mathematically using only one spatial dimension. For example, a linear motion is that of a ball thrown straight up and falling back straight down. In physics, circular motion is rotating along a circle and a circular path or a circular orbit. It can be uniform, that is, with constant angular rate of an object, and non-uniform, that is, with a changing rate of rotation. Rest. What is the definition of rest? A body is used to be static or at rest with respect to surroundings when it does not change its position with time. So rest means sthir. Motion. A body is said to be in motion with respect to surroundings when it changes its position with time. Then this change of position with respect to time is called motion. Displacement. Sharon Kakabole. The change of position of an object with respect to its surrounding in a definite direction is called displacement, which is denoted by the dimension is capital L, unit is meter. Now, what is the speed and velocity? The speed is a scalar quantity that refers to how fast an object is moving. So, speed can be thought of the rate at which the object covers the distance. So, an object with no movement at all has a zero speed. Now, what is the velocity? Velocity is a vector quantity that refers to the rate at which an object changes its position. So, velocity is a vector quantity. Now, what is speed? The rate of change of position of a body with time is called speed. Speed is a scalar quantity. So, speed equals to what? Distance by time. B equals to d by t or h by t. Dimension will be L per t, and speed, unit of speed will meter per second. Now, what is velocity? The velocity of a body is the rate of change of displacement with time, that is distance traversed by a moving body in unit time in a definite direction is called the velocity of the body. So, velocity is a vector quantity. B equals to what? Displacement by time or distance by time. Dimension will be L per t, and dimension all, remember that dimension always expressed with capital letters and units with small letters. Unit will be meter per second. This is actually difference between speed and velocity. Okay, you must know. Now, what is the acceleration? Acceleration, the rate of change of non-uniform velocity of a body with time is called acceleration. So, if the initial velocity of a body is u and final velocity is v, then the change of velocity in time t will be v minus u. So, rate of change will be what? V minus u by t. The rate of change of velocity is the actually acceleration. So, I equals to v minus u by t. So, unit will be what? Rate of change of non-uniform velocity is called acceleration. This is why velocity unit divided by time, meter per second square. Now, equation of motion. First equation, b equals to u plus at. B equals to final velocity, u is the initial velocity, a is the acceleration, and t is the also time. So, a relation bit among final velocity, acceleration, and duration of time. So, let a body with initial velocity u in uniform acceleration a. Let the final velocity is v. So, the change of velocity in time t is v minus u. We know that the rate of change of velocity is the acceleration. So, I equals to v minus u by t, and by cross multiplication, v minus u equals to at. So, b equals to u plus at. So, b equals to what? Final velocity, u equals to initial velocity, a is the acceleration, and t is the time. If there is no initial velocity, then u equals to 0. In that case, putting u equals to 0 here, b equals to at. So, second equation of motion, relation among displacement, final velocity, and duration of motion. S equals to what? U plus v divided by 2. This will be 2 actually. This will be 2, v plus u by 2 into t. Now, let a body with initial velocity u moves a distance as with uniform acceleration. Since the body moves with uniform acceleration, the average velocity will be the average of initial and final velocity. Average equals to what? U plus v by 2. So we know average velocity equals to what? Displacement by time. So S by T. S by T equals to what? U plus B divided by 2. In this case, S equals to what? Displacement equals to U plus B divided by 2 into T. This will be 2. Remember that. Now, third equation will be what? S equals to ut plus half at square. And let the initial velocity of a body be u and uniform acceleration is e. Let it attend the final velocity be in time t. Let it describe and or distance as during time t. The displacement is s. Then the average velocity b of the body will be b equals to s by t. So by cross multiplication, s equals to b bar t. Okay. Again, the body is moving with uniform acceleration. The average velocity will be b plus u by t. Just putting the value of b bar here. Actually, this will be also b bar. Okay. So we get s equals to b plus u by 2 into t. Now, again, we know that the rate of change of non-uniform velocity is called acceleration. So a equals to b minus u by t. In that case, b equals to u plus a t. Just putting the value of b in equation 3. This is the equation 3. Okay. Just b plus u by t. Now fourth equation, b square equals to u square plus 2s. Similarly, you can also derive this equation. That the initial velocity is u and uniform acceleration is a. This is actually a printing mistake. And final velocity is b. Then the body describes a distance s in time t. The mean velocity will be, average velocity will be b bar equals to s by t. So s equals to b bar t. Now again the body mass, since the body masses with the uniform acceleration, which means the velocity will be the arithmetic mean of the initial and final velocity. So b bar equals to u plus b by 2. Now putting the value of b bar in equation 1, we get this relation. Again, we know that the rate of change of non-uniform velocity is the called acceleration. Equals to b minus u by t, t equals to b minus u by a. Just putting the value of t in equation 3, we get u plus b equals to 2. Remember this is the printing mistake. This is the 2. B plus u plus b divided by 2. Okay, this is not t. So what is momentum? Momentum is the product of the masses of a body and its velocity. If the masses of a body is m, the velocity b, then the momentum can be expressed as p equals to m. It's vector quantity, and this is the dimension of momentum, and this is the unit kg meter per second. Now what will be the force? You must now Newton's laws of motion. You must know the laws of motion, inertia, and this is the Newton laws of motion. In 1687, Sir Isaac Newton gives the laws of motion. First law: everybody continues in its state of rest or of uniform motion in a straight line until an external force is applied to its body. That means what? এই মহাবিশ্বের প্রতিটি বস্তু স্থির থাকবে এবং গতিশীল বস্তু গতিশীল থাকবে যদি না আমরা বাইরে থেকে একটা ফোর্স অ্যাপ্লাই না করি। This is the first law of motion. Second law: the rate of change of momentum of a body is proportional to the applied force, and it takes place the direction of the straight line along which the force acts. This is the second law. বলবেগের পরিবর্তন হার প্রযুক্ত বলের সমানুপাতিক, এবং এই বর্বে যেদিকে ক্রিয়া করে বর্বেগের পরিবর্তন সেদিকে ঘটে। This is the second law of motion. Now third law that to every action there is an equal and opposite reaction. So প্রত্যেক ক্রিয়ারই একটা বিপরীত ইকুয়াল এবং বিপরীত প্রতিক্রিয়া রয়েছে। Now another is inertia, the tendency of a body to preserve in its state of rest or of uniform motion for all time to come, or the property to preserve its state is called inertia of body. কোনো বস্তু স্থির থাকতে চাওয়া অথবা গতিশীল থাকতে চাওয়া যে প্রবণতা, সেটাকে বলবো আমরা inertia. There are two types of inertia of rest and inertia of motion. The tendency of a body at rest to remain at rest is called the inertia of rest. Inertia of rest, and this is the example we must know. কোন একটা গাড়ি যখন স্থির থাকে তখন হঠাৎ করে চলা শুরু করলে আমরা কিন্তু পেছনের দিকে হেরে যাই। এটা পেছনের দিকে হেরে যাওয়াটা হচ্ছে inertia of rest. Okay. Inertia of motion: the tendency of a body in motion to keep the motion uniformly for all time to come is called the inertia of motion. গতি জড়তা: গতি জড়তার একটা এক্সাম্পল হচ্ছে কোনো গাড়ি হঠাৎ চলমান গাড়ি হঠাৎ করে ব্রেক করলে তখন আমরা সামনের দিকে ঝুঁকে যাই। তার মানে গাড়িটা গতিতে ছিল, আমরাও গতিতে ছিলাম, তা আমরা গতিতে থাকতে চাইছিলাম, এই জন্য আমরা সামনের দিকে এগোচ্ছি, সামনের দিকে ঝুঁকে পড়ছি, সেজন্য এটার নাম হচ্ছে গতি জড়তা, ইনার্শিয়া অফ মোশন। The tendency of a body in motion to keep on motion uniformly for all time to come is called inertia of motion. So you must know F equals to ma, force equals to mass multiplied acceleration. Let a body of mass m moves with uniform velocity u, initial velocity, or constant with a constant force F acting on a body in the direction of velocity for a time t. Increases the velocity, let the velocity after the time t will be v, that means final velocity. So initial momentum equals to mu and final momentum mv. Change of momentum, rate of change of momentum with time t will be mv minus mu. So rate of change of momentum would be mv minus mu divided by t. M common, but acceleration equals to a equals to b minus u by t. This is square, just putting this value b minus u by t equals to a, so we get ma. But according to the Newton's second law, the rate of change of momentum is proportional to the applied force. Okay, ma proportional to f. So m equals to what will be kf. K is the constant proportionality. If we take m equals to 1 kilogram, a equals to 1 meter per second square, then we get the definition of Newton. So what is Newton? If any body has 1 kilogram mass and their acceleration is the 1 meter per second square, then these types of the amount of force is called 1 Newton. So putting the value of K in equation 1, then we get the force equals to ma. So loss of motion, actually loss of inertia also equals to ma, and action reaction. And Newton's law says many people do not know what they mean or simply do not to believe what they mean. So Newton's laws of motion, first law is this: an object at rest will stay at rest, and an object in motion will stay in motion at constant velocity unless another external force is applied to it. So second law, the force equals mass times acceleration. Third law, for every action there is an equal and opposite reaction. Now first law of motion, it is also called laws of inertia. An object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. So this is the first law. Inertia is the tendency of an object resist changes in its velocity, whether in motion or motionless. These pumpkins will not move unless acted on by an unbalanced force. So if we take away a pumpkins, then we all will move. Another one is first law: once airborne unless acted by an unbalanced force, gravity or air fluid friction, okay, it will never stop. Another example: unless acted upon by an unbalanced force, this golf ball would sit on the tee forever. So this will not act it otherwise if we don't apply any force. So why then we do observe everyday objects in motion slowing down and becoming motionless seemingly without an outside force. Object on earth, unlike the frictionless space the moon travels through, are under the influence of friction. Friction means torsion. So what is the unbalanced force that acts on an object in motion? There are 4 types of friction. One is sliding friction, rolling friction, fluid friction, static friction. Sliding friction means ice skating, you must know about this. Rolling friction means bowling. Fluid friction, air or water resistance, and static friction will be initial friction when moving an object. Sliding a book across a table and watch it slide to rest position, the book comes to a rest because of the presence of a force. That force being the force of friction, which brings the book to a rest position. This is the example of friction. Now, Newton's first law and you. Suppose you are driving a car, and don't let this be you wear seat belts. Because of inertia, objects, including you, resist changes in their motion. When the car is going 80 km per hour, is stopped by the brick wall, your body keeps moving at 80 meter per hour. This is why there will be an inertia here. Now, second law, F equals to ma, you must know about this second law. The net force of an object is equal to the product of its mass and acceleration. F equals to ma. F means force and product of mass and acceleration. So, and this is also called the rate of change of momentum is called is proportional to the applied force. Okay. Now, second law, when mass is in kilogram and acceleration is in meter per second square, then the unit of force is the Newton. Remember. So 1 Newton is equal to the force required to accelerate 1 kilogram of mass at 1 meter per second square. So second law, how much force is needed to accelerate 1400 kilogram car 2 meter per second square? Write the formula F equals to ma and fill in the given numbers with it. Then we get the solve the problem. This will be 2800 Newton. Okay. Now you must know net force, mass in kilogram, acceleration. So net force will be 10, mass kilogram 2, and acceleration will be F equals to ma. Just applying F equals to ma. Now the second law proved that the different masses acceleration to the earth at the same rate but with different forces. We know that objects with different masses accelerate to the ground at the same rate. So 10 kilogram mass and this falling. So the falling the acceleration due to gravity will be 9.8. This is why 98 Newton. Now you can calculate this by the equation F equals to ma. M is the acceleration here for the falling bodies. পড়ন্ত বস্তুর ক্ষেত্রে acceleration হবে acceleration due to gravity. That means acceleration due to gravity means what? This will be অভিকর্ষজতা. Okay. So 9.8 equals to, you must know, 1 kilogram in 9.8, 1 meter per second square. Now, now about the Newton's history of discovering these laws. Check the understanding. What acceleration will result when a 12 Newton net force applied to a 3 kilogram object? A 6 kg objects. This you can solve easily. Okay. Now, force is the push or pull that causes a change in the motion of an object. Okay. This is the gravity and this is the electricity, static electricity. When you rub with a comb, your hair will be electrified with the static or electrons. So this static electricity will be produced there. And this is also friction. Due to friction, this is the magnetism. Now third law, for every action there is an equal and opposite reaction. According to the Newton, whenever object A and B interact with each other, they exert forces upon each other. When you sit in your chair, your body exerts a downward force on the chair, and chair exerts upward force on your body. So third law, there are two forces resulting from this interaction. A force on the chair and other force is in your body. So when you sit down with a chair, then these two forces are called action and reaction. যখন তুমি কোনো একটা চেয়ারে বসে থাকো, যখন চেয়ারও তোমাকে একটা ফোর্স দিচ্ছে আর তুমিও একটা ফোর্স দিচ্ছ, ইকুয়াল এন্ড প্যারালাল, এই জন্য তুমি বসতে পারছো। নাহলে কিন্তু তুমি সহ চেয়ার সহ মাটিতে ঢুকে যেতে। এই জন্য তুমি যে ফোর্সটা দিচ্ছ এটা অ্যাকশন, চেয়ার যেটা দিচ্ছে সেটা হচ্ছে রিঅ্যাকশন। Newton's third law in nature. Consider the propulsion of a fish through the water. A fish uses its fins to push water backwards. In turn, the water reacts by pushing the fish forward, propelling the fish through the water. যে মাছ যে কিভাবে চলাচল করে সেটা। The size of force on the water equals the size of the force on the fish. the direction of the force on the water is opposite to the direction of the force on the fish. Now flying gracefully through the air, birds depends on Newton's third law. This is actually another real life example of Newton's third law. And as the bird pushed down on the air with their wings, তাদের wings দিয়ে পাখা দিয়ে যখন এয়ারকে একটা ফোর্স দেয়, the air pushes their wings up, তখন এয়ারও একটা ফোর্স দেয়, then gives them lift. তারা উঠতে পারে. When consider the flying motion of a bird flies by wings. The wings of a bird push air downwards. In turns, they are reacts by pushing the bird upward. So this is the real life examples of Newton's third law. Other examples of Newton's third law: the baseball force, the bat of the left, the bat forces the ball to the right. So this is the one is action, another is reaction. Another one, consider the motion of a car on the way to a school. A car is equipped with wheels which spins backwards. As the wheels spins backwards, the grip the roots and pulls the root backward. Another one, the reaction of a rocket in application of third laws of motion, airplane, rocket, etc., using third laws of motion. So this is another example of Newton's third law. So Newton's laws of motion also have another real life example. An object at rest is at rest unless an external unbalanced force acts on it. So the Newton's first law of motion applies to the both objects in motion and objects at rest. So this is the example when you're sliding in a park. This is the actually example of inertia for Newton's first law. So this first law also called the laws of inertia. Second law of motion also, this is the laws of acceleration also. And we also have F equals to ma, we have discussed this. And for every reaction there is an equal and opposite reaction. This is also another example. Let's study rocket works to understand Newton's third law. This is the action. Rockets going out the giving out the gases, and due to this action, reaction will be here. So this is the rocket, reaction will be moving towards the direction, and this is the backward direction. The rocket action is to push down on the ground with the force of its powerful engine, and the reaction is that the ground pushes the rocket upwards with an equal forces. So this is another example. So we have discussed, we have review of this Newton's laws of motion. This is the background of discovering Newton's laws of motion. English scientist and mathematician famous for his discovery of laws of gravity. So discovered the 3 laws of motion. Today these laws are known as the Newton's laws of motion. So this is the quote of Newton's, Sir Isaac Newton's. And this is the 3 laws. Number 1 laws, this, what does this means? Actually, basically, we have discussed this one. An object will keep doing what it was doing unless acted on by an unbalanced force. So what is meant by unbalanced force? This is the meaning of the force on the book are unbalanced. The table pushed upward on the book, gravity pushed downwards on the book. And another example in our real life. A saucer ball is sitting at rest. It takes an unbalanced force of a kick to change its motion. So this is another real life example. 2 teams are playing tug of war. they are both exerting equal force on the rope in opposite direction. This balanced force results in no change of motion. Newton's first law is also called the laws of inertia. We have discussed it. Inertia means this, the tendency of an object to resist changes in its state of motion. And first law, so the more example in our real life, powerful locomotive begin to pull a long line of a box cars that were sitting at rest. Since the box cars are so massive, they have a great deal of inertia and it takes a large force to change their motion. Once they are moving, it takes a large force to stop them. অনেক বড় লরি তখন এটাকে সরাতে হলে অনেক বড় ফোর্সের দরকার। So another one, on our way to school, a bug flies, একটা মাছি যদি বা একটা মৌমাছি যদি fly করে into our windshield. Since the bug is so small, it has very little inertia and exerts a very small force on your car, so small that you don't even feel it. Important, interesting example. Okay, a book is sliding across a table, slows down and stops because of their force of friction. If you throw a ball upwards, it will eventually slow down and fall because of the force of gravity. Another one is in our outer space, away from the gravity and any source of friction, the rocket ship launched with a certain speed and direction would keep going in that same direction and at that time speed forever. Newton's second law, we have discussed in S.H.M. Acceleration, a measurement of how quickly an object is changing speed. This is the, what does it mean? So if you double the mass, double the forces. If you double the acceleration, you double the force. Okay. Now what does it F equals to ms means? Something very massive, high mass that's changing speed very slowly, like a glacier, it can still have great force. This is the example. Sometimes very. So Fa equals to ma basically means that force of an object comes from its mass and its acceleration. Something very massive, high mass, it's changing speed very slow, low acceleration like a glacier. It can still have a great force. Sometimes very small, low mass that's changing speed very quickly, high acceleration like a bullet. Okay, should এটা গুলি এটা কিন্তু স্পিড বেশি but mass খুব কম. They can still have a great force. Something very small changing speed very slowly will have a very weak force. So this is another example of second law. Now third law, for every reaction there is will be equal and opposite reaction. What does this means? Actually, we have discussed this meaning. Now think about this. What happens if you are standing on a skateboard or a slippery floor? Push against a wall, you slide in the opposite direction. So another example of this is the slippery. In rainy season, we always face this problem. Why does it hurt so much when you stub your toe? When your toe exerts a force on a rock, the rock exerts an equal force back on you too. The harder you hit your toe against it, the more force the rock exerts back on your toe. That means আমরা যে একটা পাথরকে যখন আমি পা দিয়ে একটা ফোর্স দেব, পাথর আমাকে কিন্তু ইকুয়াল একটা ফোর্স দেবে. This is the review. Newton's first law, Newton's second law, Newton's third law. Inertia means the tendency of an object to resist changes in its state of motion. Acceleration is this also. Force, velocity. So from this point of view, Newton's laws of motion we have to discuss about force and mass. Actually, force means what? Force or pull required to change an object's motion vector, show magnitudes and direction. And so 4 forces known in the universe. One is electromagnetic force, strong force, gravitation, weak forces. You must know about the force unification theory. 3 forces unified. Dr. Abdul Salam from Pakistan, he got a Nobel Prize for that. 3 forces unified. This is the force unifying theory. Now another force is the actually gravitational force. This is a very weak force. So this 4 force will be very important in physics. Now there are 2 main types of forces. One is contact, another is field. Field force, this one, and contact force, this. Now contact force what exists when an object from the external world touches a system and exerts a force on it. Think about a book on a table. You'll understand this contact force will be acted along that. Another one is an object can move without something directly touching it. Gravitational force is a field force. And can you think another field of forces? Magnetic fields, electric fields, nuclear fields, etc. Now, examples of contact force: friction and tension. So, mass equals to inertia. Also, this is the example of what in mass is immeasurable of an object with inertia. This is the example. Okay, and this is the also application of Newton's third law and second law also I understand. Now, this is the background of Newton's laws of motion. This is the first one. This is the application, real life example. Now, what means by the unbalanced force? You must know, we have discussed it also. Okay. Now, what is gravity and gravitation? Actually, gravitation or gravity is a natural phenomenon by which physical bodies attract with a force proportional to their masses. Gravitation is most familiar as the agent that gives weight to objects and with mass and causes them to fall to the ground and drop. So the definition of gravitation and gravity: in the solar system, the attraction between any 2 bodies except the Earth and any other bodies is called gravity. For example, attraction between the sun and the moon is gravitation, and but between the Earth and the book is gravity. So gravity is itself a kind of gravitation. Now Newton's laws of gravitation. Newton's laws of gravitation states that every point mass in the universe attract each other with a mass, with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Suppose 2 bodies of masses m1 and m2 are suspended from each other by a distance d. Then, if their force is between these 2 bodies with force is m, so F is the force attraction between them according to the laws of gravitation. Force is proportional to the m1 m2 divided by d square. So F equals to capital Z m1 m2 divided by capital Z is the universal gravitational constant, where F is the force between the masses. This is the gravitational constant. M1 is the first mass, and M2 is the second mass. For the distance between the masses, value capital Z equals to 6.673 into 10 to the power minus 11 Newton meter square per kg square. So here, acceleration due to the gravity is Z. The rate of change, increase of velocity of a freely falling body on Earth due to force of gravity is called the acceleration due to gravity. It is denoted by Z, and standard value of Z is 9.80665 meter per second square. The value of Z in the polar region is 9.83217. So this is the, now what is the mass? Mass is the measure of the amount of material in an object, and weight is the gravitational force acting on a body of mass. Transforming the second laws of motion, we can find the weight equals to mz. M equals to mass of a body, and C is the acceleration due to gravity. Okay. Now work power energy. Actually, the work done on an object is the product of the average force on its and distance traveled in the direction of the force. Work equals to what? The product of the force and displacement of a body application along the direction of the force is called work. W equals to Fs. Dimension is this and unit also this. The power will be also this. The work done by a person or a source per unit time is known as power. So power equals to work done divided by per unit time. This is the same energy. The capacity of doing work of a body is known as the energy. Energy is a scalar quantity and dimension is the same as the power. So dimension equals to ml square per t square. This is the unit of dimension of force. And form of energy, there are two form of energy is 9 form. Mechanical energy, heat energy, sound energy, light energy, magnetic energy, electric energy, chemical energy, nuclear energy, solar energy. The mechanical energy are two types: potential energy, kinetic energy. This is the definition of potential energy. So potential energy equals to mg's. M is mass, g is acceleration due to gravity, and is the vertical height. Similarly, kinetic energy, you can also find out the value of kinetic energy. This is the actually half mv square. The principle of conservation of energy: every energy can neither be exerted or destroyed, but it can be transferred from one form to another form. It is called the principle of conservation of energy. The total energy of the universe is constant and unchangeable. Okay, various types of gravitational and potential energy. Okay.
So, summation F equals to that means total net force equals to ma, and work done also energy conserved useful when the work done by force. Now impulse momentum also can be written like this. Now the basic symbols: linear and angular motion, displacement, velocity, acceleration, inertia, kinetic energy, and net force for linear force and momentum. So linear for displacement can be denoted by x, but in angular displacement, velocity v, angular velocity momentum, acceleration a, angular acceleration is alpha, inertia is m, and angular inertia inertia of motion or rotation is a half mv square. Okay, so in this way we can now for a rotational body, that means when it will be positive or negative, z is the actual axis. Whenever we talk about the rotation, it is multiplied rotation or axis. Okay, rotational axis. Now this is usually called z axis. We usually omit the z subscripts for the simplicity. Counter clockwise increasing theta is usually called positive, and clockwise or decreasing theta is usually called negative. So you have to remember this concept for rotational bodies. So now angular acceleration, angular velocity, and angular mass. So and rotational inertia, the resistance to change in rotation motion, tau equals to I alpha, whereas the angular inertia of mass and A is the acceleration. Actually, torque equals to moments of inertia multiply angular acceleration. This is the alpha. Now equals to mr square. Then the moment of inertia equals to mass multiply distance from axis squared. And this is the different types of moments of inertia. We have proved some in our class. Now, what is the actually angular motion? If the total torque on a object is zero when it does not rotate or rotates at a constant angular velocity. Physical linear motion, what will be? If the total force of an object is zero, then it does not move or it is in linear motion with constant velocity. So you have to remember this. Inertia can be represented as m, and rotational second law of momentum. This is the linear momentum and this is the rotational. Conservation, P is equals to constant, that means total force equals to 0. For rotational, L equals to constant. If tau equals to 0, then torque equals to 0. Kinetic energy half mv square and kinetic energy half I omega square. Actually, have derived this in our class, and we also derived this one in our class. This is the rod with axis through end. Okay, rod with axis through center, that means in the middle part of the rod. These two A and B calculated in our class, finding moment of inertia for the rod. This is the example, physical example, real life example of angular velocity. So if the net torque not a system is zero, the total angular momentum of the system is conserved. That means L omega, where L equals to a vector quantity, I is the tensor, and omega is the vector also. This is the also example of rotation, and this is also example of rotation in our real life. So rotational velocity is a vector. Use the right hand rule to find the direction. This is the right hand rule for finding the direction of angular velocity. This is also real life example of rotation. Before wheel is flipped, this, after wheel is flipped. This is the negative because in the negative direction, and this is also LW, this one, and this is also LS. So now, what is the rotational motion or angular displacement? This is in the simplest kind of rotation. Point on a rigid object, move on circular path around an axis of rotation. And this, the angle through which the object rotates, is called the angular displacement. You have to remember this definition. What is the angular displacement? This is given by del theta. Axis of rotation is this, and this is a disk and reference line, and this is the radical line from which started the rotation. If the changed rotation is del theta, then del theta can be calculated with this. Del theta equals to theta minus theta naught. Theta naught is the initial angle and theta is the final angle. Okay, so this difference will give the angular displacement. So when a rigid body rotates about a fixed axis, the angular displacement is the angle swept out by a line passing through any point on the body and intersecting the axis of rotation perpendicularly. This is the actually radical line from where it will start the rotation. Is the axis of rotation. The angular displacement is positive if it is anti-clockwise or counterclockwise, and negative if it's clockwise. Remember it. Anti-clockwise hole positive or clockwise hole negative. You have to remember this one. SI unit of displacement is radian. Okay, so this can be calculated as in radian arc length divided by radius S by R. Arc length means this is the arc length, any portion of the circumference which subtended an angle through the with the center. So this is called arc length divided by radius. So this can be also calculated as theta equals to twice pi r divided by r. That means twice pi radian. So twice pi radian equals to 360 degree. This is the adjacent synchronous satellites. With the satellites, we are uh, connected in the whole world, in the global village. So this is actually in case of rotation. So satellites are put into the orbit which radius is this. So if the angular separation of the two satellites is 2 degree, find the arc length that separates them. Easily you can be calculate with this formula. It equals to arc length by radius. So this equals to 0.0349 radian. Just s equals to r theta, arc length, this s, that means distance between two satellites, can be found r theta. Okay, this meter and this radian. So 920 miles or 1.48 into 10 to the power 6 meter. So the change the angular displacement equals to theta minus theta naught. How do we describe the rate at which the rate of change of angular displacement is called angular velocity? Okay, so definition of angular velocity is rate of change of angular displacement. That means angular displacement divided by elapsed time. So this can be written omega bar equals to rate of change of displacement change time del theta by del t. SI unit of angular velocity is radian per second. So this is the real life example. A gymnast on a high bar. A gymnast on a high bar swing through two revolutions in a time of 1.90 second, and the average angular velocity of the gymnast. So this can be calculated as like this: minus 12.6 radian. That means negative. That means clockwise. This is why this is the clockwise rotation. Okay, so we get negative angular velocity minus 6.63 radian per second. The changing angular velocity means that an angular acceleration is occurring here. So average angular acceleration equals to change in angular velocity divided by elapsed time. So angular acceleration can be denoted by alpha. So alpha bar average means what? Alpha bar equals to omega minus omega naught divided by t minus t naught. That means rate of change of angular velocity divided by rate of rate. So assign it will be radian per second squared. A jet reviving its jet engine. Okay, this is the real life example of angular acceleration. As seen from the front of the engine, the fan blades are rotating with the angular speed of minus 110 radian per second. As the plane takes off, the angular velocity of the blade reaches minus 330 radian per second in a time of 14 seconds. Find the angular acceleration. We can easily find the angular acceleration of this jet. So just the rate of change of angular velocity divided by taken time. Now we have to remember these equations for linear motion: displacement, acceleration, final velocity is b, initial velocity is b naught, elapsed time is t. Then we can use this equation of motion. Okay, and this is the angular for the angular motion. We can use this linear equation of motion. For angular velocity, we use the first one, and for the alpha is the angular acceleration. And second one is can be calculated angular displacement, t is time. Okay, this is the actually quantity we have used in rotational motion and linear motions. So this is the distinguished chart of angular rotational motion and linear motion. This is the reasoning for you. Blending with a blender. This is the real life example of in everybody's kitchen. So axis of rotation is this, and this is the blender, and this is the plug. If we choose on, the blades are hurling with an angular velocity of plus 375 radian per second when the puree button is pushed in. So the angular acceleration has a constant value 1740 radian per second square. Find the angular velocity of the blades. This is the real life example to find out the angular velocity of the blades. This one, this is from the given values, and we have to find out the angular velocity omega. Just using this equation, we can find out the value of omega easily. Similarly, the tangential velocity is bt and tangential speed is the curly bt. Okay, so stationary is skater or pivot. This is the skater. In the time of skating, this has happened. So we can find out the tangential motion s by t. S means what? Arc length r theta divided by t. So r into theta by t. So omega is equals to theta. So tangential motion equals to r omega. That means linear velocity equals to radius multiply angular velocity. So similarly, linear acceleration equals to this one. We have derived it in our class. Alpha equals to what? Omega minus omega naught divided by t. That means rate of change of angular velocity is called angular acceleration. So linear tangential acceleration or linear acceleration equals to radius multiply angular acceleration. For example, a helicopter blade has an angular speed of 0.50 revolves per second and angular acceleration of 1.30 revolve per second square. For a point one on the blade, find the magnitudes of the tangential speed and the tangential acceleration. Actually, we have to find out the linear speed, linear velocity, and linear acceleration. So just using the same formula, we get the bt equals to r omega. Okay, this is 122 meter per second. So similarly, you can find out the angular acceleration and tangential acceleration. So angular acceleration is this, and tangential will be, or linear acceleration will be this 24.5 meter per second square for this helicopter. This is a helicopter problem. Similarly, acceleration equals to linear velocity whole square or tangential velocity whole square divided by r. So radius. So b equals to r omega. That means we get r omega square. So for uniform circular motion, we can use this equation. And this is the uniform, and this is the non-uniform. Okay, acceleration is the constant, but in non-uniform, acceleration divided by into two parts. One is horizontal, on the other, another is in perpendicular or tangential. So this is the uniform circular motion. This is the non-uniform circular motion. Now let's discuss thrower. So starting from rest, the through or acceleration that discussed to final angular speed of this and before releasing it during the acceleration. So find the magnitudes of the total acceleration. So we get from this example, angular acceleration equals to this 182 meter per second square. Similarly, tangential acceleration will be also found 45 meter per second square. We use the Pythagoras theorem, we can determine the overall magnitudes of the acceleration. Just okay, taking components of linear acceleration, divided into two parts, tangential and horizontal acceleration, acceleration along the horizon. So this is the linear velocity, b equals to r omega. The tangential speed of a point on the edge of the tire is equal to the speed of the car over the ground. This may be explained as by the length by distance or distance by time. That means actually the velocity. Rate of change of displacement is called velocity. So for calculating this, the acceleration of the vehicle can be analyzed in a similar fashion to the linear and tangential velocity. Thus, linear acceleration equals to r into angular acceleration. For example, an accelerating car. Starting from rest, the car accelerates from 20 seconds with a constant linear acceleration of 0.800 meter per second square. The radius of the tires is this. So what is the angular which each wheel is has rotated? So we can easily find the value of omega using the angular equation of motion. Now we'll discuss torque and rotation. Actually, what is torque? Force is the action that creates changes in linear motion. For rotational motion, the same force can cause by very different results. A torque is an action that causes object to rotate. A torque is required to rotate an object just as a force is required to move an object in a line. So torque is created by force, but it's also depend on where the force is applied and the point about which the object rotates. For example, a door pushed at its handle will easily turn and open, but a door pushed near its hinges will not move as easily. The force may be the same, but the torque is quite different. This is the real life example of us when we are opening door while entering the room or in classroom. So center of rotation, the point of or line about which an object turns its center of rotation. For example, a door center of rotation is its hinge. Hinge মানে কবজা, আমরা বাংলায় কিন্তু কবজা বলি, দরজার কবজা, সে কবজার উপরেই ডিপেন্ড করবে। A force applied far from the center of rotation produces a greater torque than a force applied close to the center of rotation. Torque is created when the line of action of a force does not pass through the center of rotation. So the lever arm is the perpendicular distance between the line of action of the force and the center of rotation. So calculating torque is this is the formula, tau equals to lever arm or radius or distance multiply force in Newton. This is the for the direction, clockwise negative, counterclockwise or anti-clockwise is positive, to find out the direction of root torque. Now we can calculate torque in two sets and B parts. Unit of torques, Newton meter. A torque of 1 Newton meter is created by a force of 1 Newton acting with a lever arm of 1 meter. That means radius equals to 1 meter. We can try at home this example to find out the value of torque. Similarly, when an object is in rotating equilibrium, the net torque applied to it is zero. For example, if an object such as seesaw is not rotating, you know the torque on each side is balanced. This is the real life example of, or in any park we see this example. So rotational equilibrium is often used to determine unknown forces. Any object that is not moving is in irrational equilibrium and translational equilibrium. This is then another example. We can find out the value of the forces. This is also example for finding the forces when the body is in equilibrium position. So for vertical equilibrium, we can use F equals to Fb equals to 1250 Newton. This is given. This is the total force. This is Fa and this is Fb. So rotational equilibrium. So we can find out easily. This is another one. This is also example you can solve to find out the rotation. This is the tau equals to Fd cos 30 degree. You can try this. This is also example of another example. This is a very interesting example. You'll understand better. So torque can be written as like this. Force is perpendicular to the radius, and this is the radius, and this is F. So we can use tau equals to a perpendicular radius multiply force at an angle theta. We can find also the torque by using this equation, tau equals to r f sin theta. This is the dot product. So net torque can be calculated as like this: total torque from both sides of rotation. So rotational motion, center of mass, effective point that all forces act upon, and this is also called balance point. Now, what is inertia? Linear mass unit kilogram. So angular moment of inertia, rotational inertia, describe the description of mass for a given object. An object tendency to continue or to rotate or remain at rest. And this can be denoted by I equals to mr square different. So this is the moment of inertia, single object moving, I equals to mr square. We have proved this in our class. So for circle and hoop, I equals to mr square, and disc for solid cylinder, I equals to half mr square. We have also derived this one. For a sphere, 2 by 5 mr square. And for rod through the center, 1 by 12 mr square, because we have derived this one in our classes. And rod through the end, 1 by 3 mr square. Now kinetic energy also, half mb square. We have proved this one in our classes. Angular kinetic energy for rotation, half I omega square. We also proved this relationship in our classes. Momentum, linear momentum can be denoted by P equals to mb, mass multiply velocity, and angular momentum L equals to moment of inertia multiply angular velocity. So conservation of angular momentum can be denoted by this. Conservation of angular momentum is same, that is constant, no change. So back to the nature of angular quantities. Displacement, velocity, acceleration, force, momentum, etc. These the same quantities are vectors in the angular frame. Right hand rule, we have to use right hand rules for that. Now we'll discuss the overview of rotation on simple harmonic motion. So first of all, spring, for a spring, restoring a force for proportional to the displacement. This is the Hooke's law. F equals to minus kx and E equals to half kx square. So first of all, Young's modulus. Where does k come from? Simple harmonic motion and springs revisited. So what is the springs? Actually, Hooke's law, the force exerted by a spring is proportional to the distance the spring is stretched or compressed from the relaxed position. This is denoted by Fx equals to minus kx, where x is the displacement from the relaxed position and k is the constant of proportionality. This one is the relaxed position. This is the equilibrium point for the spring. Now here at this point x equals to 0 and the force also 0, but in this direction if we pull this spring like this, so what is the force spring when it is stretched as shown below? F greater than 0, F equals to 0, F equals to 0 is the relaxed point, okay, and F less than 0. This is the another distance. So this distance the opposite of the force. This is why minus is used here. So if F less than 0, then by Hooke's law we get Fx equals to minus kx, and this force will be less than 0, and this distance x displacement will be positive. So for the relaxed position we get x equals to 0, but if the spring shrink, or if we push the spring about the distance x less than 0, so where x is the displacement from the relaxed position and k is the constant proportionality. So in that case we can find the one. Now potential energy in a spring, by Hooke's law, the force is conserved. Force along the y-axis and the displacement along the x-axis. So force will be constant. So the work done, this is the work done, and work done can be calculated minus half kx square. So work done only depends on the initial and final position. Okay. So how we can define the potential energy of the spring? Half kx square. Now what is the Young's modulus? The spring equal for this spring, by Hooke's law we can find F equals to minus k. What happens if cut the spring in half? Decreases, same, or increases? So if increases, k is inversely proportional to the length. So we can define strain and stress like this. So here L is the Young's modulus. So why Young's modulus depends on L, length. Now what will be the now what will be the simple harmonic motion? Here we have to use vibrations. First of all, vocal cords when singing or speaking, okay, then string or rubber band. Simple harmonic motion, restoring force proportional to the displacement. Springs look like a spring, F equals to minus kx. So a mass on a spring oscillating back and forth with a simple harmonic motion, amplitude say a plot of displacement x versus time t shown in the. So at what point during its oscillation is the magnitudes of the acceleration of the block biggest? When x equals to plus a maximum displacement, x equals 0, d0 displacement, the acceleration of the mass is constant. So for this simple harmonic motion along x-axis time t, and this is the maximum displacement plus a, and this is the negative. So using the linear force F equals to ma, so spring simple harmonic motion, we get x equals to 0. So in the 0 position, we can calculate x equals to a, and maximum acceleration is negative. So now if the displacement is 0 and velocity is the negative and acceleration also 0 at 0 displacement position, but here the maximum length x is the displacement a and velocity is 0. Now in the third one, this is the negative x equals to minus a and velocity is 0 and maximum acceleration is mx. So this position is the x equals to a position, and this position is the x minus a position, and this is the equilibrium position. So maximum displacement a and their minimum displacement. So in three position, the simple harmonic motion can be seen here. Now in fourth position, the spring uh, displacement is 0 and velocity is the maximum. Acceleration is here 0. And in the fifth position of a spring, maximum displacement is x equals to a and velocity is here 0 and maximum acceleration is negative. So energy, we can find out the energy of the spring where the mass m is attached to it. So a mass is attached to a spring and set to motion. The maximum displacement x equals to a. So in that case, this is the kinetic energy. This is the potential energy. So total work done. So total work done is 0. Energy plus k is constant. So energy equals to, you must know, kinetic energy and potential energy. Kinetic energy half kx square and potential half mv square. So at maximum displacement x equals to a, velocity is 0. So energy equals to half k a square. So at maximum displacement energy is half k a square. So at 0 displacement x equals to 0, the energy is half mv square. That means in that case we get the total energy is the same. So potential energy and kinetic energy are same. So velocity equals to square root over k by m a. So this is the a practical example for the previous example. So if x equals to 0, all the spring potential energy is converted into the kinetic energy. So the velocity will be greatest at this point. So velocity will be greatest. Now at this point, the energy changes from spring to kinetic energy, but is not lost. So this is the correction. The energy of the system is constant. Now, when does moving in a circle have to do with the moving back and forth in a straight line? So this is the actually simple harmonic motion in wave. This is the plus r maximum displacement, and we can convert it into a full cycle whose radius is r, and this is the x equals to r cos theta. That means this is the along the x-axis. So so it is related to cos, because cos equals to base by hypotenuse. So base equals to what will be? Base means what? X. Equals to hypotenuse means r. Okay. So cos theta. So this can be calculated by this length. Remember it. Just this transforming to circle, we can easily find this displacement. So since theta equals to omega t, we can use r equals to cos omega t. This is the simple harmonic motion and circle combination of these two. This is the actually real life example of simple harmonic motion, which making wave and circle. So simple harmonic motion can be written as x equals to a displacement cos omega t, and velocity can be written as minus a omega, just differentiating this equation, we get this minus a omega sine t, sine cos differentiation sine, but omega t differentiation with respect to t will be omega. This is why omega is multiplied to it. Similarly, we can get the acceleration taking the differentiation of velocity with respect to time, we get this one. So maximum displacement is a, so maximum velocity will be omega a. So maximum velocity is a, because cos 0 equals to 1. Okay, maximum velocity will be what? A omega. Okay, a omega. And maximum acceleration a omega square. So period t equals to second per cycle, and frequency f equals to 1 by t cycle per second. This is the definition of angular frequency, can be written as also like this. So for a spring, omega square equals to k by m. This is the, okay, we can use the formula of simple harmonic motion by this also. So this is the example for solving. This is the 5 cos omega t, just comparing with the standard form, a standard equation of simple harmonic motion. We get easily 5 cos omega t. Another example, this will be 0.03 joule, total kinetic energy equals to potential energy plus kinetic energy at time t equals to 0, x equals to 5, so b equals to 0. So easily can be calculated, energy 0.03 joule. Similarly, maximum speed of the block also can be found like this. Okay, b equals to 0.14 meter per second. Similarly, you can find this example. So summary, we can use this for a spring like this, simple harmonic motion. So now the differential equation of motion, of simple harmonic motion, using f equals to ma for the spring, we have ma equals to minus kx. So but acceleration equals to d square x by dt square. This is the rate of change of velocity with respect to time, is called acceleration. So the simple force equation, it can be written as just putting the value of a here, m d square x by dt square equals to minus kx, or d square x by dt square equals to minus k by x equals to x. So an object moves in a simple harmonic motion whenever its acceleration is proportional to its position and has the opposite sign to the displacement from the equilibrium. So acceleration, you can find out this acceleration uh, in a previous way. So note that the acceleration is not constant, unlike our earlier analytic calculation. So for the maximum displacement a, the initial acceleration is minus k by m, but as it passes through the 0, acceleration falls to 0. So for the displacement x equals to 0, it only continues past is an equilibrium point. The block for the minimum displacement minus a, the acceleration becomes plus k by m. So analyze the model simple harmonic motion. What is the units of k by m in this? So these are 1 by second square, which can be regarded as a frequency squared, omega square equals to k by m. So when the equation becomes a equals to minus omega square x, so a typical way to search a differential equation is to simply search for a function that satisfies the requirements. So we have solved this differential equation of simple harmonic motion, and we solved it. We found a solution like this. This is actually a solution we have derived in our class. A solution to the differential equation is xt equals to a cos omega t plus phi. We have derived this equation in our classes and solved some real life example also. Here a is the displacement, omega is the angular velocity, and pi are the angle constants. So as the amplitude, maximum position, omega is the angular frequency, which can be written as root over k by m, and with the phase constant or initial phase angle, and phi are determined by the initial conditions by using this one. Okay, so the motion equation for simple harmonic motion, this x equals to a cos omega t plus pi, and differentiating, we get the rate of change of displacement with respect to time, that means velocity, this minus omega a sin omega t. Similarly, acceleration can be found by differentiating the velocity with respect to time, that means the rate of change of velocity is called acceleration. So the velocity, if the velocity is 90° about the phase with the displacement, and the acceleration is 180° about the phase with the displacement. So this is the maximum displacement, okay, and maximum velocity, this one, and this is the maximum acceleration. So from these three figures we can compare with these three equations. So initial conditions for the time t equals to 0, x equals to maximum displacement and velocity is 0. This means phase is 0. The acceleration reaches extremes of plus minus omega square a, that means at plus minus a displacement. The velocity reaches extremes plus minus omega a at distance, displacement equals to 0. Similarly, for example 2, we can find this one. Now consider the energy of simple harmonic oscillator. The kinetic energy equal to half mv square, spring potential energy half k x square. This also can be calculated. Then total energy can be calculated half k s square. I means the maximum displacement. So transfer energy. So total energy is constant here. So simple pendulum, we can also use the same differential equation for the simple pendulum, where the tangential acceleration or linear acceleration equals to radius multiply angular acceleration, so L alpha. So L d square theta by this is the differential equation. So this is another differential equation, this is used in simple pendulum. So for the simple pendulum, angular velocity is root over z by L. Okay, using the same formula for simple harmonic motion in simple pendulum. So this is the angular position change equals to angular displacement equals to maximum theta cos omega t plus pi. So this is the torsional pendulum. This same differential equation is used here. This theta by dt square equals to minus k by l theta. Now, what will be the damping? When a bell ring, it is transferring energy stored in its oscillation to the sound by moving the air around. So it does not work against frictional forces and is said to be damped. So this is the definition of damped of a spring. Whenever frictional forces acts on an oscillator, its total energy will diminish with time so that its amplitudes decay to 0. So damping means this is the various displacement uh, of the spring. So the heavier the damping, larger frictional forces, the greater the rate of decay. So displacement will become 0. So damped oscillation, so after displacement decreasing. So damped oscillations are when the amplitudes of the oscillations becomes gradually smaller and smaller as energy is taken out of the system. So deliberate damping. Damping is deliberately introduced into some system to prevent continuous oscillations. An example is car shock absorbers. So this one, free and forced oscillations. Free oscillations means the system oscillates without any force applied, and its frequency is its natural frequency, and there is a little or no damping. So forced acceleration means the system responds to a regular periodic driving force like continuity pushing a child on a swing. So resonance means if the frequency of the applied force equals the natural frequency of the system, resonance occurs. When this is when the system oscillates with maximum amplitudes. Similarly, if we push the child on the swing, each time they reach maximum amplitudes, their oscillations amplitudes increases. If you push when they are halfway back towards you, their oscillation amplitudes decreases. So this is the good example of resonance. A good example of resonance is when a singer sings a note of frequency equal to that of the natural frequency of a wine glass, like this. So, and this is the real life example of resonance and engineering. This is the due to resonance, the breeze breakdown. Okay. Now, critical damping. This is the critically damping in figure. Overdamped is the less carved, but critically damped is more carved. The system, when displaced and released, returned to equilibrium without overshooting as quickly as possible. The useful in car shock observers, cars must go into the resonant oscillations when they go over bumps in the roads. So now variation of the amplitudes of a forced oscillations and driving frequency. This one the example of like this. So now we can review the periodic motion is the self-repeating motion. It's also called harmonic motion. Oscillation means periodic motion in certain direction. And period means what? A time duration of one oscillation. Frequency what? The number of oscillations per unit time. SI unit is hertz. So this is the Henry Hertz, who is the founder of this unit. So F equals to 1 by T. Now motion of the spring mass system, this is the Hooke's law for this, for the equilibrium position. And we get F total force equals to 0. So this is the review. This is also simple harmonic motion. And this equation we have derived as a solution of differential equation of simple harmonic motion. Okay, this is the for various time period the displacement amplitudes A. What is the amplitude? The magnitudes of the maximum displacement in either direction. So phase is the angle of cos omega t plus pi. This is the, and phi is the phase displacement for different phase. Okay, with different colors. Angular frequency omega, and if phi equals to 0, we get this result. So omega equals to twice pi by capital T, and omega equals to 2 phi f, 1 by t equals to f. This is why. Okay, so period t equals to twice by omega, rate of change of angular velocity. So this is the velocity of simple harmonic motion, just differentiating this solution of the differential equation of simple harmonic motion. We get similarly acceleration also found, and we get also force by using Hooke's law. T equals to twice by root over m by k. We have derived this formula in our class. So energy consumption, potential energy, and kinetic energy also found, just putting the value of x. So this is the omega square equals to k. So total energy can be found. Okay, so this is the figure of total energy. Okay, this is the simple pendulum restoring force tau, Newton's second law. Using Newton's second law, we can find out the alpha. So angular acceleration equals to minus mgl by is. On the other hand, we get omega is angular velocity is approximate to root over this one. So we get easily derive, we can easily derive the formula capital T equals to twice by root over L by Z for the symbolic harmonic motion. So this is a design of physical pendulum. Simple harmonic motion. This can be, this is the phase, and this is the after time t. This is the xt equals to a cos omega t plus del. Velocity will be this, and acceleration will be this. So damped pendulum, there is this damping force Fb equals to minus Bb, where damping constant is the B, and this is the figure for damping constant. Now force oscillations and resonance. So this one is the example of resonance. Okay, this is the actual intermediate system. Intermediate systems cannot be solved by the simple application to the equilibrium conditions. So that is the elasticity, definition of elasticity, stress and strain. This is the all deformation results from a stress deforming force per unit area, and deformation are described by a strain unit solution. This is the tension and Young's modulus. We have discussed about this Young modulus. Okay, thanks to everybody. I hope everybody